So we'll pick up with continuity. All right, so after we finish the concept of continuity, we're going to go back to working some limit problems using those limit laws. And then pretty much after that, we're going straight into derivatives. So we would have covered all those concepts. All right, so let's look at what we mean by what we say a continuous function is. Now, when you did college algebra, you would have gotten a more basic definition. Do you all remember what we say a continuous function is from college algebra? So it's basically a function. So when you graph it, there is not going to be any break in the graph, like any asymptote or any hole. So if you're drawing it with your pencil, you can draw it without even having to lift your pencil, right? But in calculus, we're basically looking at continuity at a particular point. So the function may not be continuous everywhere, but it may be continuous at some point or at some parts of the graph. And that's what we look at when we talk about continuity in calculus. So we say that a function is said to be continuous at A. Notice I'm being specific, right? If this exists, if the limit as x approaches A of f of x is equal to f of A. And I'm going to break it down for you into 3 parts so you can see what I'm talking about. So what we're saying is that these 3 conditions must be met. And as I said, it's summarized here, but I'm just going to break it up. Now, f of A must be defined. The limit as x approaches A of f of x must exist. And when does the limit exist? Whenever the right-hand limit is equal to the left-hand limit. Don't forget that. And finally, this is the main part that ensures continuity, because this is basically a combination of those first 2. So we're saying that the limit value must equal to the function value. And that's the only way it's going to be continuous. So the limit value must equal to the function value.
So like, let's say the limit is as x is approaching 3.
Right.
And so that whole thing has to equal f of 3.
Yes.
Okay.
Yeah, they must be the same. So let me give you an example. So let's say you have a graph. And we look at some of these in our last class. And let's say this is 3. And we have something like this. And let's say the function goes like that here. And it goes like that here. Just an idea. I'm going to give 2 examples. I'm going to put another one here. And then let's say at 3, we have a hole here instead. And it looks like this. And then let's say we have a point here, right? Let's say this is 1. And let's say here at the hole, we have, let's say that's 4. Now, if you're looking at the first example, let me use a different color. What do we notice happen here? What's the limit? Look at the left-hand limit. What's the left-hand limit? Oh, let me put a value here. Let's say this is 4 as well. All right. So in this particular case, what is the limit as x approaches 3 from the left? 4, right? What about the limit as x approaches 3 from the right? It's also 4, very good. And what is f of 3? What is the function value when x is equal to 3? Where does it meet the graph at? At 4. So do you notice that they're all equal? So the limit value is 4, because left hand and right hand, they're both 4. The function value is 4. So it means, therefore, that this is continuous at x equal to 3, because we see that all the conditions are met. So pretty much you can summarize it in just saying all of this, right? Because all of this is just breaking it up. Because we're saying that the limit exists, so left and right hand limit must be equal for the limit to exist, and then it must equal to the function value. Now let's look at this particular example here. In this particular case, the limit exists, right? I'm gonna write shorten it for this one. The left hand limit is equal to 4. Everybody seeing that? The right hand limit as x approaches 3 is also equal to 4. That's where the hole is. But what is the function value?
1.
Very good. F of 3 is equal to 1. Are they the same? No. So is it continuous or discontinuous? Discontinuous. So this function here is not continuous. Right, at x equal to 3. And you can look at the graph and tell, because look, what do we have right here? We have a gap. You all seen that? Right. Once you have a break in the graph, it's not going to be continuous at that point. If you have an asymptote at that point, it's not going to be continuous either. But you do need to know these definitions, because sometimes when we're solving problems, we have to apply the definition to solve for some unknowns. And I'll do an example so you can see what we're talking about. So all you need to remember is that for continuity, the limit value at the point must equal to the function value. That ensures continuity. That's the main thing to remember. All right, let us go ahead now and do some examples so we can get confident in what we are doing. Example number 1. So below is the graph of f of x, and we want to determine if the function is continuous at these given values. So let's start with x equal -3. So that's right here. And we're going to give a reason for each of these. Is it continuous at -3? No. Why? We see a what? A gap. There's a gap, right? The left hand and the right hand limit, they are not the same. So this is no. Not continuous. So when it's graphical, you can actually see the graph and know whether or not it is continuous. What about at whenever x is -1? No. Right, because we also have a gap there as well. So that's no. We have a hole in the graph. Everybody seen that? And then the function value is different. What about at x equal 2? No, because there is a hole. So even though the limit exists, there's no function value. It's discontinuous at that point. So it's not. What about when a is equal to 4 or x is equal to 4? Yes. Yes, it's continuous. As you can see, the limit is 5 and the function value is also 5. So that's how we can tell whether or not the function is continuous or discontinuous at a point. All right, let's look at another example, example 2. So we're given a function and we're asked, is f of 3 defined? Oh, I actually saved my answer. That should have been blank. So, all right, so we already know that it's no, but can anybody tell me why it's no?
Because the bottom is going to be 0.
Very good. You're going to end up having 0 upon 0. So this is undefined. So that's why it's no. How do you know that the limit is equal to 6? What did they do to evaluate the limit? You all remember that sometimes we need to do what? How do we get to cancel the denominator at times? We have to do some form of start with an F. FA. You have to do some form of factorization, right? So what we have in the top here is a difference of two squares. So this is going to be the limit as x approaches 3. Now, what's the square root of 9? What do we square to get 9? 3. So this is the same thing as x minus 3 in one bracket and x plus 3 in the other bracket. And we're dividing by x minus 3. Now, anything can be canceled?
Yeah, the top left and the bottom.
Very good. So those can go. Now, the fact that you get rid of the denominator, you don't have any issue now to substitute. If you plug 3 into this reduced function, what do we have remaining? 6. Very good. That becomes 3 plus 3, which is equal to 6. So that's how they get the 6 here. So the limit value is 6. What can we conclude? Is the function continuous or discontinuous?
Discontinuous.
Yes, and for what's the reason?
Because f of 3 is not defined.
Very good. F of 3 is not defined. Very good. So it's discontinuous. All right. So we can only stress it enough to say that it's only going to be continuous if the function value is equal to the limit value. And in this case, the limit does exist, but the function value is not the same as the limit. In this case, the function value at 3 doesn't exist. So the function is not continuous. There would be a hole in your graph whenever x is equal to 3. So if your denominator can cancel, you're going to produce a hole in the graph. Bear that in mind. If it cannot be canceled, then you're going to have a vertical asymptote at that value. So those are the difference, right? Mm-hmm. All right. And if you want to be more formal, this is the reason. We say that the limit as x approaches 3 of f of x is not equal to f of 3. So that means it is discontinuous. If you want to be more formal, you don't have to state that, but that's really what is happening. All right, we're going to do another example. Let me just remove my answers first, so I don't take away your ability to think. Why is this not allowing me to remove my answers? Okay. All right, looks good. All right, so here we have another example, and these are known as piecewise functions. And what do we mean by a piecewise function? It's a function that is defined differently for different parts of your domain. So think of it as a function in pieces, just as the name suggests. All right, so let's look at this here. Is f of x defined everywhere? Yes or no? Take a minute to think about it before you answer. You can look at the graph to help you, because I went ahead and I graphed it. Let's see what's happening here. The only place we may have issue possibly would have been at 1. Yes, you do see there we have a gap in the graph at 1, right? Yeah. And also at 2. But do we have function values at 1? We have it right here. So it's defined. It may not be continuous at 1, but it's defined, as you can see that. When x is 1, y is also 1. Does that make sense? Right? And then another part we would have an issue is right here at 2. But as you can see, we do have a function value at 2. What is it? 3. It's 3. So yes, it's defined everywhere. So once you look at where you have hole or gap and you can get a function value, then you know for sure that it's going to be defined everywhere. Because we have no issue out here, because this continues all the way on and on. we have no issues to the left of 1 as well, because there's no more break in the graph.
So if it was just like,
Mm-hmm.
if they happen to be like both empty holes, it would be undefined, right?
Very good, right. So it would not be defined at 1 if both of them were just open circles,
Gotcha.
right. All right. So let us do number 2. You're going to explain to me why f of x is not continuous, even though it is defined everywhere.
Because there's breaks.
Very good. Because we have holes in the graph at when x is 1 and when x is 2. Very good. Because you have a break in the graph, so it's not continuous everywhere. So this is because of holes or break in the graph. And if you want to be more more formal using your math language, you can describe it in terms of the limits. You could tell that the limit value from both directions would not be the same. So the left-hand limit, there it's not equal to the right-hand limit, right? Especially at 1 and 2. Everybody seen that? When x is equal to 1 and also when x is equal to 2. So if you look at the limit as x approaches 1 from the left and the right, you'll see that the right hand and the left hand limit, they are not equal. If you want to be more formal, you could describe it like that as well. And for continuity, we have to ensure that left and right hand limit are equal to the function value. Now, so this is a good question on a multiple choice problem. They could ask you, is it possible to have a function that's defined everywhere but not continuous? And that will be yes, as you can see in this example. So even though it's defined everywhere, it doesn't mean that it has to be continuous. What did they say to you though? If the function is continuous everywhere, is it defined everywhere?
Yeah.
Very good, yeah. In that case, it is. And I already went ahead and did the sketch for you, so that's good to go. Now let's look at some theorems. And these are, you're gonna need most of these for your multiple choice. Now, if you have two functions, f and g, and they're both continuous at some point A, then the following will also be continuous. If you add them, so the sum of two continuous functions will also be continuous. If you subtract them, that will also give you a continuous function. If you multiply them, you'll also get a continuous function. And if you divide them, you will also get a continuous function. If you find a composite function, meaning you put one inside the other, like g inside of f, that will also be continuous. And if you multiply any of these functions by a scalar quantity, like let's say you multiply the function by 2 or 10, whatever your scalar is, then that will also yield a continuous function. So any operation with your continuous function will also produce another continuous function. And what we're going to do, we're going to provide the proof for one of these. So we get into the arts of being formal in math by doing some proofs. So we not only say things, we're going to prove that this is true. So let's look at the proof for the first one. But I haven't taught you guys the laws of limit yet. Well, you'll learn it now before we get there. All right, so all we want to show, right? We want to show that the sum of two continuous functions will also be continuous. So what I'm going to use is my definition of continuity. You all remember what the definition says? Is that the limit, right, must be the same as when I plug in the value into the function. So that's all I'm using. So the limit as x approaches f of f plus g is going to equal the same as f plus g of a. So let's prove that this is true. Now, by laws of limit, and this is your first law that you will learn, I'll go over them shortly. Whenever you're finding the limit of the sum, it's also the sum of the limit. You can always split them. So this is the same here as having the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And what I use here is laws of limit. So that's one of the laws of limits. If you find the limit of the sum is also the same as the sum of the individual limits. You can always split them or combine them to get the same result. Now, what's the limit as x approaches a of f of x? This is the same thing as what? Just plug it in because there's no break here. So that's just going to be f of a plus, what's the limit as x approaches a of g of x?
G of a.
Right, it's a continuous function, so it has to be g of a. Because you're told that the individual functions are continuous. So that's the g of a. Now, is f of a plus g of a the same thing as f plus g of a?
Yeah.
Yeah, it's the same thing. Which is the same thing as f plus g. All these I did in algebra, this part of it, of a. And so your proof is done. And as a math student at this higher level math, whenever you do a proof, you just draw a little box and you shade it to say, yeah, I got this done. You don't have to, it's just. A lot of mathematicians like to do that. Do you think you guys could provide the proof for number 2? To do the difference instead? Follow the same step and try to get the difference. Prove that the difference will also be the same.
Oh, okay.
So if you look at this, you're doing the same thing. That's instead of where you have plus, you're going to be subtracting instead. So try it and see if you get it. How is it going for you guys?
I might have got it wrong, but
You want to try to write it on the board?
no. I'm not gonna lie, I kind of just followed the steps of the first one, but just with subtraction. And
Yeah.
so I got it at the same thing.
Yeah.
Oh, so it's the same thing.
Yeah.
Oh, okay.
Right.
I
Yeah.
overthink.
Right.
This is my
So-
problem with math. I overthink everything.
Yeah,
I'm sitting here, like,
right.
thinking, I'm like, there's probably some completely different way I was supposed to do this.
Right. And by the way, for this course, I rarely ask you to produce a proof on like most of your assignments in the book, you realize that they're not proofs. And for tests, even if I give you a proof to do, it's usually for extra credit. If I was teaching like a course with students who are going on to be like math teachers or wanting a math degree, then I tend to teach it from a different perspective to do a lot more proofs. Here, I still try to introduce some proofs, but at the same time, I try not to really test them when I'm giving you guys tests. Right? But I still want to get you to practice to know that, hey, we can prove all of these things. So at least one or two out of the set, I'll always try to prove. And for persons who are curious, you can always Google the proofs for the others and get those done. All right, so that's it for your proof. So they're not too bad. These proofs are pretty easy, but like all the things that we're saying, we can prove them. And if you guys ever have to do a course called mathematical analysis, then it's like a proof course. You prove a lot of things that you use in math in general. It's not a walkover course. I can tell you that. Your math has to be extremely strong to excel in that course. But it helps you to appreciate a lot of things. You have some students, when you tell them things, they're like, I want to see it for myself. So yeah, go and prove it. For me, I'll just take it and accept it and move on with life. But not everybody's like that. They want to justify everything. All right, let's randomly look at some true and false questions as we wrap up this section. Any polynomial is continuous everywhere. You all know what is a polynomial?
Yeah, it's more than one like
terms being added together. And the variable must not be in any denominator as well. Like you would have like f of x equal to x squared plus 5x cubed plus 6x to the 5th power, right? So those will not have any denominator. So you're not going to have any issue as to being divided by a 0, that kind of thing. So you're going to have the function value being the same as the limit for all polynomials. So that's true. So your polynomials will be continuous everywhere. That's a true statement.
because it's not being divided by 0.
Right.
Okay.
There's no denominator to worry about being 0.
Right.
Yeah.
It's all just one string all over one.
Right. Let's look at this one now. Any rational function, when you talk about a rational function, it means not that it can have a fraction. Like you could have 1 upon x or x cubed plus 3 upon something else. But it's saying no, any rational function is continuous wherever it is defined. True. So they're not claiming that it is continuous everywhere. They're saying it's going to be continuous where it is defined. That is true.
And it's still not being divided by 0, so that's why it's defined.
Right, because where it is defined, it will be continuous at that point, right? If it's a rational function. Not the same for a piecewise function though.
Yeah,
Okay, it can be defined based on those gaps. So if you have a piece, I think there's one on it, so let me not jump there. Number 3. Any piecewise function is continuous wherever it is defined. False, that's not necessarily true, right? So it's false. It can be, but it's not guaranteed. And this is an example. It's defined, look at when x is 1, it's defined here, but we still have a break in the graph, so it's not continuous. Right. So whereas it is true for rational function, it's not true for piecewise function. It can be defined, but not continuous. Number 4, sine x and cosine x are continuous everywhere. For those of you, well, you should have done trigonometry before. Yeah. Is that true or false?
It's true.
It is true. So your sine and your cosine, remember those waves, right?
They're just continuous.
They're continuous everywhere. What about tangent? Is tangent continuous everywhere?
I believe so.
You guys remember?
I kind of don't remember what a tangent function looks like besides.
All right, bear this in mind. Remember this identity from trig? You're going to be using a lot of identities in this course as we get deeper into it. Not so much as in, not a lot in calculus 1, to be honest. Most identities resurface in calculus 2. So it's going to be pretty light for calculus 1. Now, if you have the tangent of x, it is the same thing as sine of x upon cosine of x, right? So the tangent function can be written as a rational function in terms of sine and cos. Now, what happens if cos x is 0? We have an issue, right? So this is going to be false. It's not continuous everywhere. Any value that make cosine of x 0 would create a problem for tangent. Number 6, the following functions are continuous at every member in their domain. When you say domain, it's talking about the value of x where it's defined, right? The polynomials, the rational, the root, the trig, inverse trig, exponential, and log functions. What do you guys think? Yeah. It's continuous at every number in their domain. Yeah, so that's going to be true.
Yeah, this one.
What's that? It does?
It's a T down there.
Oh, on your sheet?
Yeah.
I forgot to remove it. Yeah, so it is true. So these are some concepts you need to remember because they are pretty helpful, right? Now let's do an example and then we're going to go over to the laws of limits. And then we will go into some computations with limits. So let's do an example. Do you all have your textbooks here today?
Yeah.
Okay. Let me write up the problem. I can't remember if this one is in your textbooks. Yeah, I'll just write it out. I'll do it on my problem. All right, so example. So you're given a piecewise function f of x and it's equal to x squared minus 4 over x minus 2 if x is less than 2. And then it is ax squared plus bx plus 3 if x is less than 3 but greater than or equal to 2. And then finally 2x minus a plus b if x is greater than or equal to 3. And you're told to find a and b if f of x is continuous everywhere. So we're going to use the definition of continuity to find the two unknowns, a and b. And this is as hard as your continuity problems will get. They're pretty easy. All right. So any idea what we can? So we are told that the function is continuous everywhere. And we want to find the unknowns A and B. So what do you think we can do to do that? What do we know about a continuous function? If the function is continuous, we know that the left-hand limit
And the right-hand limit.
they must be equal, right? And then it's also going to equal to the function value, meaning when you plug in that particular value into the function. So that's what we're going to do. Let's go ahead and look at the limit as x approaches 2, because these are the things that we have. So we have 2, and we also have 3. So we can create our definition using the limit when x is approaching 2, and it's also approaching 3 to get our equations to solve. So let's start with 2. If I look at the limit as x approaches 2 from the left, which equation am I using?
The plus.
If it's less than 2, am I using this equation or this one down here?
It's probably the first one.
Right, because less than 2 means left of 2. Does that make sense?
Yeah.
Right. So what you're looking at, so the limit as x approaches 2 from the left would just equal to, what would that be? I think we have to do some factorization. If you plug in 2 directly, then you're going to have a 0 in the denominator.
So it's going to be undefined.
It's not undefined, we can simplify it. Difference of 2 squares, remember? When you have x squared minus 4.
X minus 2.
Yeah, very good. So we can simplify this to be x minus 2.
Oh, I think
X plus 2. And then over x minus 2. So you can cancel the problem child. Anything given the problem, try to get rid of it. And what does that give us? If we plug in 2 into this, what does it give us? 4. 2 plus 2 is 4. So that's equal to 4. Now let's do the right-hand limit now. So you're going to have the limit as x approaches 2 from the right. And in this case, this is a polynomial, so you can do a direct substitution. A 2 from the right would be the equation that tells you that x is greater than 2. So it's going to be this second one, 2 from the right. So let's plug in 2 anywhere we see x. So that's going to be 2 squared is what, 4? So 4 times a would be 4a. 2b, and then plus 3. And then set them equal to each other to create your equation, because you're told that the left-hand limit must be equal to the right-hand limit since they're continuous. So we're going to end up having 4a plus 2b plus 3 must be equal to 4. And I'm going to bring over my 3 to keep numbers on one side and letters on the other side. So 4a plus 2b is going to be 4 minus 3 is 1. So this is your first equation. Equation 1. We can't solve that as yet because we have 2 unknowns and 1 equation. So we can't go anywhere with it as yet. We need to get another equation, then we can solve them simultaneously. Now, how can I get another equation? We can look at the limit now with 3 being the value that x is approaching. So we're going to examine the limit when x approaches 3 from the left, and also when x approaches 3 from the right to get our next equation. Okay. Yeah. So let's go ahead and do that. So we're going to find the limit as x approaches 3 from the left. And which equation am I using when it says 3 from the left?
Oh, wait, no, sorry, the middle one.
Middle one, right. Because that's when x is less than 3. So that's left of 3. So plug in 3 and tell me what you get. We're going to have 3 squared is 9. So that's 9a So that's equal to 9a plus 3b, and then plus 3. Right. Now also look at the limit as x approaches 3 from the right. Which equation are we using if it says 3 from the right? Right, when it's greater than or equal to 3. So that's 2 times 3, that's going to give us 6. Right, so that's going to be 2 times 3 is 6 minus a plus b. And since left-hand limit must equal to right-hand limit because they're continuous, then we're going to equate these. So we're going to have 9a plus 3b plus 3 equal to 6 minus a plus b. Now let's group everything on. I'm going to keep my letters on this side. So I'm going to bring over the a, it becomes a plus a. So we're going to end up having 10a. I'm going to bring over this b, it becomes a minus b. So we're going to end up having 2b. And I'm going to bring over this 3 because I'm keeping my single digit values on the right side. So 6 minus 3 is going to be 3. And this is my equation 2. So now we have 2 equations. Do you all remember how we can solve 2 simultaneous equations? Let me put them together. So we have 10a plus 2b equal to 3, and then we have 6a plus, no, we have 4a plus 2b equal to 1. (4a plus 2b equal to 1). You all know how we can solve these kind of equations? Yeah, you can subtract them in this case. And Brady, why would you subtract them? You're correct, but you didn't know why?
It gets rid of the 2b.
It gets rid of the b, very good. So if you subtract these 2 equations, 10a minus 4a gives us 6a. 2b minus 2b would cancel each other. And 3 minus 1 would give us 2. So we can now solve it. What is a equal to?
1/3.
Yeah, you're dividing both sides now by 6. So 2 over 6 is the same thing as 1/3. Now that you know you found A, how can we find B? Any idea what we can do?
Substitute a in for something among the equations.
Very good, yeah. Take any of your equation, it doesn't matter which one, and plug in the value of A. Which equation are you guys using? It doesn't matter which one.
The bottom one, I guess.
This one right here?
Yes.
All right, no problem. All right, so we are going to have 10 times 1 over 3 plus 2b, and that's equal to 3. So that means that 2b equal 3. I'm going to bring this over. So it's going to be minus 10/3. 10 times 1/3 is the same thing as 10 over 3. 10 times 1 is 10, and then the same denominator. Now, subtract this and tell me what you guys get. (10 over 3 is the same thing as 3 and 1/3. So I think we're going to have negative 1/3. Yep. And then divide both sides by 2. What's negative 1/3 divided by 2?
Negative 1/6.
Negative 1/6, yep. So A is 1/3 and B is negative 1/6. There's one like this in your assignment on continuity. So you can follow this example to do it. That's how you do it. Just examine the left, the right, equate them. And there are times when you may have to do it twice, like what we did. So you can get two equations and then you solve the two simultaneous equations. And this is going to be on your 2.5 homework. So now we're going to go back to 2.3 when you look at calculating using limit laws. And that's the final thing we're going to do for today. Next week, we'll pick up with limits at infinity and also using limits for sine and cosine type functions. By right, this should have been done next week, but as I said, I don't normally teach in the order of the book. I just do what I think make more sense and go in that order. All right. All right, now we're going to look at calculating limit using limit laws. Laws of limits. What's going on here? Okay. So we have laws of limits. Number one, and some of these you're going to know already because we kind of used them when we did those proofs earlier. If you have the limit as x approaches a of f of x, this is just going to equal to f of a. And that is if f is continuous, right? Right. If f is continuous. That's pretty much your definition of continuity. That's going to be the limit. So if the function is continuous, like your polynomial and so forth, you can just go ahead and plug in the value. That will be the same as the limit. Number two, if you have the limit as x approaches a of some constant times a function, c is a number, some constant, whether 5, 10, -2, whatever that is, then this is going to equal to the constant times the limit of the function. So you can always pull out the constant and multiply it by whatever the limit is. Number three, if you have the limit as x approaches a of f of x, plus, it can also be minus. I want to merge them together. F of x plus or minus g of x. Then you can also split them. So the limit of the sum or the limit of the difference would be the same thing as the sum of the limit or the difference of the limits, respectively. So this would be the same thing as the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. You can always split them. If you're adding, you can split the limit. If you are subtracting, you can do the same. And I'm going to do one last one. There are many others, but we don't need to go through them. By now, you can see that you can pretty much do any operation with your limits. You can always pull them out and all these things, split them. All right. Now, if you have the limit as x approaches a of f of x times g of x, this is when you will find the limit of the product. It's the same thing as the product of the limit, so you can always split it as again. So this is going to be the limit as x approaches a of f of x times the limit as x approaches a of g of x. We can always do that. Let me just put this last one there, the quotient one when you divide. If you have the limit as x approaches a of f of x divided by g of x, this is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. Now, are there any restrictions? You're dividing, so what must g of x not be? 0, right. So g of x must not be equal to 0. So those are your laws of limits, and we are going to look at some examples. And we have some special cases that we're going to look at. We may get to those next week. We are going to look mostly now at the regular scenarios. All right, are we ready? Evaluate the following. Number 1, limit as x approaches -2 of x squared minus 4x plus 7. That's the first one. Now, this is a polynomial. What did we say about polynomials again?
It can be simple.
Yeah, they're what everywhere? Polynomials.
Oh, continuous.
Yeah, they're continuous everywhere, so you can just go ahead and do a direct substitution. So this one is pretty easy. You're just going to plug in -2 anywhere you see x. Do that and tell me what you get. What's the result? Did I say 19? Yeah. So if negative, that's 4 here plus 8, 12 and 7, 9, 19. Yeah. Right, so 4, -2 squared is 4. -4 times -2 is +8. So add those and then 7, 19. Number 2, we want to look at the limit as x approaches 5, the square root of 6x cubed minus 7. That's another easy one. That's a direct substitution as well. So by the way, bear in mind, like problems like these, when I have square root, the only issue, you do not want to have a negative inside your square root. That's the only thing to pay attention to.
Wait, I'm sorry. What did you say?
Oh, like square root problems, you do not want to have a negative in your square root. Right. However, in the real number system for these. All right, so do a substitution and tell me what you get. So that's going to be the square root of 6 times
125.
125, and then minus 7 from that. Square root of? Oh, you give me the final answer? That's fine. What is the
Oh, I
final
wasn't giving you the final. I said that was 750.
Oh, it's right here is 750? Oh, okay. And then 750 minus 7.
743.
And then find the square root of that and tell me what you get. $27.25. All right, so that's good. All right, we're going to step it up a little to some more mature problems. I'm not going to kill you guys too much. So this book I'm pulling the problems from is from I was doing calculus 1 as an undergrad student, and this was back in Jamaica. And I had a professor who was like super smart, and he would give us like the hardest problems ever. I think it built us though, because we were like math majors, so I appreciated that. But seeing that you guys are not gonna be pursuing a degree in math, I'm not gonna kill you guys. But at the same time, you'll get quality problems to challenge you as well. Yeah. So I'm just warning you. All right, let's look at this one. As I said, I'm stepping it up a little bit. This one may not be too difficult for you guys, though, from what we did previously. What if we have the limit of, let's say we have the limit as x approaches -7. In my denominator, I'm going to have x plus 7. In my numerator, I'm going to have let's see what I want to have here. All right. What do you guys notice about your denominator in this case?
It's that if you put -7 in it, then it's going to equal 0.
Right, so we're in some problems, right? So it means that we need to do some factoring or something to cancel the denominator.
With multiplying.
Multiply it
Multiply by 7.
by 7.
Well,
That's not gonna help us that much. Mhm.
Can you factor the top so that it'll be different than x cubed minus 49x and try to get the x off the other one and get the other one down to x squared?
You can do that because notice what's common to both terms in the top? The x, right? Yeah. So you can do that. So this would be the same as the limit as x approaches minus 7. So you're saying here that I can factor out x from the top? Yeah. So if I factor out x, what leaves?
X squared minus 49.
Right, x squared minus 49. And then we still have over x plus 7. Now, can we factor x squared minus 49?
Yes, do x plus 7 and x minus 7.
Right, difference of 2 squares. Good. Oh, I'm out of space. I need a new page. All right, so we're going to have the limit as x approaches minus 7. Then we have x at the top, and x squared minus 49 would be x minus 7, x plus 7, all over x plus 7. What do you guys notice now? Can we cancel anything?
Yeah.
Yeah, these are gone. So now we don't have to worry about any issue in our denominator. You can go ahead now and make a direct substitution, because what you have remaining is a polynomial, so to speak. So let's go ahead and simplify. So we're going to have minus 7 times minus 7 minus 7, which is minus 7 times minus 49. Oh, no. I would be arrested in a math prison for that. So it is minus 7 minus 14. And that's where you get carried away on test 2. What's minus 7 times minus 14?
Negative. No.
Positive. 7 times 14?
Is 98.
98, right. So that's going to be positive 98, right. And so that's going to be your limit. Yeah, so these are, we're subtracting. So we owe 7, then you owe 7 more, you're owing 14, right? And then you multiply. So look out for these. Sometimes you may have a quadratic that you need to factor. So during your spare time, watch a little video on YouTube to remind you to factorize quadratic, because you're going to see some of these problems coming up in your homework as well. I'm trying to do at least all right, here's another one that I want to give you guys. All right, another example. What if we have the limit as x approaches minus 2, and then we have x plus 2 over x cubed plus 8. Any thoughts on this one? If you do a direct substitution, do we have a 0 in the denominator?
No, but we have a 0 in the numerator, which means the whole thing would be 0, right?
If the 0 is only in the numerator, then we're fine. But look at what's happening to the denominator of that one. If you take negative 2 and cube it, what happens? What's that? So that means negative 2 times negative 2, that's positive 4, then times negative 2 again,
It's negative
-8. So you'll also have a 0 in the denominator. So we have an issue. Well, what can we do? Because we can't factor the top. It's already simplified. What do you think we can do in that case?
Say we can take
Mm-hmm.
one x off the top and one x off the bottom. But I feel like
We couldn't do that because it's not common to both terms that we can just factor out. Right. But that's a good thought though. Any other suggestions? Kate, what do you think? Yeah, but what can we do before we factor the bottom? Yeah, you're pretty good. So if you can factor the bottom, you may be able to cancel out something just the same, yeah. But do you know how we can factor out x cubed plus 8?
we can factor out the top and bottom by x plus 2, right?
Yeah. But so if you divide x plus, well, I gave away the word, right? What we can do is do like a polynomial division, right? To extract a factor of x plus 2 from x cubed plus 8. All right, so we could do a polynomial division. So let's leave this for now and see what we can do, right? Now, let's say you have x cubed plus 8, and you want to divide it by x plus 2. All we have to do here, just rewrite this function. Rewrite it as 1 over x cubed plus 8 over x plus 2. So if you flip the order of a fraction, just divide 1 by that result. It doesn't change anything. Let me show you why, in case anybody is curious. Look at this, everybody. If you have a over b, that's the same thing as 1 over, flip this, b over a. Because if you have 1 divided by b over a, what did they tell you in elementary school when you divide two fractions? You change to multiply and do what with the second one? Flip it. So this would be 1 times a over b, which gives you about the same thing here. So you can always do that.
So you multiply out x plus 2 and then flip the x cubed plus 8 over. So we'd end up just multiplying x plus 2 and x cubed plus 8.
No, what I want to do is to divide them. Because we have a technique in math called polynomial division that we can use to divide a polynomial by a lower degree one. So I don't know if you guys remember, you did this in college algebra. So just write down the coefficients. So the coefficient of x cubed is 1. There's no square term, so put a 0 as placeholder. There's no x term, put a 0 as placeholder as well. And then put back your 8. So all you want is the coefficients. So 1 is a coefficient of x cubed. There's no square term, there's no linear term. So leave those as 0 as placeholder. And then write back your constant. And then I'm dividing by, if I'm dividing by x plus 2,
It's going to be
what am I dividing by?
1 and 2.
You're going to divide it by minus 2. And I'll explain to you why we use minus 2 and not positive 2. Because if you have a factor, let's say x plus 2 is a factor, right? So you're going to have x plus 2 equal to 0. So if you solve that, x is actually equal to negative 2. Right.
Gotcha.
Just like when you solve your quadratic, you always say, I'm going to erase this, but let's say you have something like this. I'm just trying to refresh your algebra. Let's say we have x plus 3, like after you factor your quadratic, x plus 2 equals 0. X is not equal to 3. What is x equal to? No, not 0. So this means that you're going to have x plus 3 equals 0, or x plus 2 equals 0. So what is x equal to here?
Negative 3.
Or x equal?
Negative 0.
Right. So the sign always changes by the actual value of x. That's what I was trying to bring up.
Gotcha.
Yeah. Let me just erase this. That's what this is, a refresher. All right, so let's go ahead now and do some polynomial division. And by the way, this is actually called synthetic division. When you do polynomial division, you actually divide it using the actual x's and variables. And I can show you if you guys are interested. It's a little more tedious, but it's one of these days I'll show you. Yeah.
This one you just drop in and
Yeah, so with this one, you get us work with numbers, no x's. That's why a lot of persons prefer the synthetic division over the polynomial division. So this is actually synthetic division. Let me correct that. So you always just bring down the first. Right, you multiply on this side and then you add on this side. So you're gonna say 1 times -2
Is -2.
-2, -2 plus 0
Is -2.
right? -2 times -2
Is 4.
4 plus 0
4.
4 times -2
-8.
-8 plus 8.
0.
So there's no remainder. So this is now your new quadratic that is formed. And this was a cubic, so your answer that remains is going to be 1 degree less, which will be a quadratic. All right, so let's see what we have now when we divide these two. So we will now have the limit as x approaches -2 of 1 over. Now, we divided this to get this.
So
This would mean x squared, right? And then minus 2x, you always put it in order. And then a constant would be left, so that's plus 4. Now see if you can plug in -2 without getting a 0 in the denominator. If you can do that, then that's going to be your limit. If not, then the limit does not exist. Because there's nothing else we could do since it's already in its simplest form in the numerator. What happens when you plug those in? I think I got 1 over 12. Anybody got that? 24? Let's check. I could be wrong, so let's check. -2 squared is 4. -2 times -2 is also 4, and then plus 4. So 4, 4, 4, that's 12. Yeah, 1 over 12.
For whatever reason, I was thinking of 4 for the first, like 4 or -4 squared.
Oh, I see.
So I
Yeah.
put 16.
Oh, I got you. Yeah.
I put 1 over 16 the first time, but that's because for whatever reason my mind processed 4 4s instead of 3 4s.
Yeah, that happens.
So my brain is
Trust
sort
me,
of just like,
it happens to all of us at times. So that's another way how you guys can do those. So it may involve some factoring or things like that. Now I have a proof for us to do, another example. We want to prove that the limit as x approaches 0, the absolute value of x is equal to 0. Now they are telling us that it's equal to 0, but they want us to prove it. So we are going to use a definition to prove it. How will I prove this, that the limit actually exists? It means that we need to examine the left-hand limit and also the right-hand limit. Now, does anybody remember from algebra the definition of your absolute value? So if we have the absolute value of x, you all remember what the definition is?
Distance away from.
Yeah, it's the distance. So we know that it's always going to equal to x whenever x is positive, or negative x if x is what?
Less.
Right, if x is less than 0. And we're going to close this as well. If x is, whenever x is greater than or equal to 0, right? We're going to close it. Right? And then it's negative x if x is less than 0, right? So that's how we look at the definition. And the reason why we use negative x for when x is less than 0, because let's say x is negative 10, you would have like negative 10, which would eventually give you a positive, because we know that distance cannot be negative, right? So that's why we use that definition. So if I want to find the limit as x approaches 0 from the left, which value am I using?
The negative x.
Right. Then that's just going to equal to minus 0. But do we have a negative 0? No. So it's just going to still be positive, just going to be 0, right? Right. A 0 cannot be negative. I don't like the look of having a negative 0 there, so I'm just going to put minus x. That's the definition I'm using, which is just going to be 0, right? And then let's look at the limit as x approaches 0 from the right of absolute value of x. And that's just going to be, which definition am I using if it's right? The top one, right? So that's x. And that's just going to be 0. What do you notice now about the left and the right hand limit? They're equal. So that concludes the proof that the limit as x approaches 0, absolute value of x must be equal to 0. And the proof is done. If you were to ask if it is continuous, what would you say at 0? If you plug 0 here, what do you get? You also get 0, right? So this would also be continuous if you were asked, but he didn't ask us for that because the limit value would equal to the function value. But they didn't ask us for that. So that's what we would have. All right, let's see what time. Oh, we still have some more time, so we can look at some more concepts. All right, let's look at some useful results. And this involves trigonometry. So this is where it gets pretty interesting. So useful results. And you're going to use these whenever you're asked to solve these type of limits. Just the black. Now, number one, if you have the limit as x approaches 0 of sine x upon x, or even if you flip it, or if you have the limit as x approaches 0 of x upon sine x, it doesn't matter the order, then they're both equal to 0. Sorry, not 0. They're both equal to 1. So bear that in mind. And you may ask, how? How can that be 1? Nobody has that question? Just think about it. I mean, if I plug 0, there's a 0 in the denominator, so that's an issue to do a direct substitution. But how do I know that it's approaching 1? Let's look at the graph. That can help us a lot. Because I'm trying not to be like too abstract with you guys. So I don't run you away from the course and then you're gonna drop it and say, Miss Terry, I need to drop the course. So I'll just show you on a graph, right?
That's what happened to the other guy who watched the video and dropped it.
No, he didn't. He actually dropped it before, so I'm not sure what happened.
He saw the name of the class. And freaked out. He's like,
Probably.
"What is
Probably.
this?"
So we're looking at what's the function again? Sine x upon x. So sine x divided by x. We're gonna just see what's happening at 0. By the way, there should be a hole here. Oh, yeah, it's actually there. Do you see that there's a hole? Because at 0, you'll be dividing by 0. So there's some form of discontinuity there. Desmos is just not showing us unless we click it. You can actually see that there's a hole there. You all can see that? Right. Now, if you notice, as x approaches 0 from the left, the function value is approaching 1. Do you see that? The hole is at 1. And what about when it approaches 0 from the right? I'm trying to, oh, my hole there. It's approaching 1, right? So it's funny that even though it's not defined at 0, but that's why limits are important, because we can see how the function behave as x gets closer and closer to 0. We see that the limit of the function is approaching 1. So remember that the limit is not your function value. It's not defined when x is 0, we know that. But what the limit tells us is what is it getting closer and closer to. So we have an idea how it behaves when it's close to that value. That's what the limit tells us, right? So even though we don't know exactly what's happening there, but we know what happens close to it. That's what the limit tells us. So we can see that this, they didn't just make up this result, it's actually approaching 1, the graph, as you can see. All right, so bear in mind this result, that if you have the limit as x approaches 0 of sine x upon x, or x upon sine x, then it's going to be approaching 1. So you can always substitute that result when you're doing these kind of limits.
So if we replace sine with cosine, would it just be -1 then?
It doesn't work for cosine. I'm getting to that. Yeah, so bear this in mind. So number 2, if you have the limit, I'm happy you asked, as x approaches 0 of cosine x upon x does not exist. The left hand and the right hand limit will not be the same, and we can graph it to show. Let's pull back up our Desmos. So we can see cosine x upon x. Look at 0, do you notice? From the left, it's approaching negative infinity. From the right, it's approaching positive infinity, so the limit does not exist. So if you have any problem with cosine x upon x, you cannot use 1 there, it doesn't exist. Right? So for cosine, it doesn't work. All right, let's look at the third result, and then we're going to do some examples. And most times when you have problems with cosine, we have to employ what we call the squeeze theorem. That can help us to get what the limit is. And I'll demonstrate it to you. It's very, very easy. All right, number 3. If we have the limit as x approaches 0 of cos x minus 1 upon x. Now, this is going to be 0. That's going to be 0. And if you graph it, you will see. You can graph it on your own time if you want. I think by now you guys trust my results because I've already showed you the graphs for those two.
Is that
Upon x.
Okay.
Yeah. So if you have cos x minus 1 upon x, then the limit will be approaching 0 for that one. So bear these results in mind. So we're going to do an example and see what happens. All right, evaluate. So we have the limit as x approaches 0, and then we have sine 4x upon x. That's what they asked us to do. In a case like this, you can always manipulate the result. And I give you the permission, you can always, you have to manipulate these kind of problems at this level in math. As long as you're not breaking any mathematical laws, you can do it. Now, based on definition, we know, this is what we know, right? We know that the limit as x approaches 0 of sine x upon x is equal to 1, right? But we have sine 4x. So it means that we need to have a 4x in the denominator as well. So the sine of the angle must be the same angle that you're dividing by. So all I'm going to do is change this to 4. But I changed the problem, right? I need to put a 4 here to cancel back the 4 that I added. Everybody's seeing like technically these would cancel, so I'm not changing the problem when I do that. Do you see why I did that? You can always do these things as long as you cancel out anything that you add. So because I want the same angle, because as I can see here, sine x upon x. So because we have sine 4x, I can't just pull out this 4, but it's inside the sine function. So what I did, I just make this be 4x down here instead, and then multiply by a 4. Because 4 upon 4 is 1, it would be cancelled anyway.
Oh, so it just ends up being 1.
Pretty much.
Okay.
But because we want it like this to apply the definition, so look at what is happening here now. What's happened to all of this limit here now, based on this result over here? Sine 4x upon 4x would be what? 1.
But it's being multiplied by 4. So
Right.
It's 4.
So it would be 4, right? They have a 4 here. So remember now we have a law of limit that says if you find the limit of a value times the function, remember that C? I think that was our third rule or something like that. You can always pull it out. So this is the same thing as 4 times the limit as x approaches 0 of sine 4x upon 4x. And of course, this is just 1. So it is 4 times 1, which is just going to be 4. So you can always pull out any scalar quantity that you have outside of the limit. That's why you multiply it. Right. If this was a test and you just put that this is equal to 4 from here, that's good enough for your full marks. But I just expanded to show you why we did what we did.
I was just kind of thinking like, since sine of 4x would just be like the actual function moved to the right 4 times, right? Is that how that works or no? Because that's what I was kind of thinking earlier. It's like if it's sine of 4x and like normally it's 1 if it's just sine x over x. But since the 4 is there, you'd just be moving it right or
No, you'll be moving it. So it depends. So if you have like a sine x plus 4, the graph would go up 4 units.
right.
Minus 4, it goes down. Now, if you multiply by a 4, you're going to have what we call, it's not going to shift it, it's going to be more like a stretch or a shrink.
Oh,
Right.
That's right. That's
Right. So that's what happens when you multiply inside a function. It will result in a stretch or shrink, but it will not be shifted from its position.
gotcha.
Right. If you have something like this though, let's say for example, you have something like this sine, and then inside you have like an x plus 4, then this is telling you that you are shifting this to the left 4 units in that case.
That's what I was I just had it kind of mixed up.
Right.
Because I saw a number inside the function. So
That's what would have happened in that case, right? All those shifts from college algebra, right? Remember them? Yeah. All right, so that's how we would do that one. All right, let's try one more. Number 2, show that the limit as x approaches 0 of sine let me get a nice problem for you guys. Let's start with a simple one. Sine 10x upon 2x is equal to is equal to 5. So they're telling you what the answer is, they just want you to show it. Could you show that? And we only have like 2 minutes to go. So what we're going to do, so when we return next class, we're going to be looking at the squeeze theorem, and then we're going to look at limits when x is approaching infinity, and that will be the end of limits before we move on to derivatives. What do you guys think about this one? So we have a 10x here. What do I want in my denominator?
5, or I'm sorry, 1.
So this is a 10x right here, right? So we need to have 10x down here. What can I do to 2 to make it multiply it by 5? So we're going to multiply down here by 5. So if I multiply my denominator by 5, what should I also do?
Multiply the numerator.
The numerator should also be multiplied by 5. So you know that all of this here is just going to be 1. Agree? Right. So it's just going to be 5 times the limit. And just plot this 5 here. You can always do that to your scalar as x approaches 0. And then we're going to have sine 10x upon 10x. And all of this is just 1. So we know that our result is just going to be 5. So that's how you would do these.